All right, we're going to cover the answers for the assigned problems for the lab from Chapter 9. Question number 1 said, under what circumstances is a t-statistic used instead of a z-score for a hypothesis test? The circumstances are we use the t instead of a z when the population variability is unknown. Remember I said that at the top of the series of videos for the lectures for Chapter 9. That's really the major difference. If we don't know the variability for the population, either variance or standard deviation, then we're going to use the sample to estimate that value. Number 6, explain why t-distributions tend to be flatter and more spread out than the normal distribution. Well, this is in a way a continuation of question number 1. What we're saying here is we know that samples are imperfect, samples contain error. So that error is going to distort the normal distribution. It's going to change the shape of that normal distribution. So because the t-statistic relies on sample variance, which is dependent on sample size, we know if sample size goes down, error goes up, and that error causes the distortion, causes that curve to get pulled out and shrink flatter. For question 14a, we're just going to do our regular 4 steps for that. So step 1, the alternate hypothesis is the treated population mean will not equal 80, and the null hypothesis is the treated population mean will equal 80. Again, our regular format that we've been doing for a couple of weeks now. Step 2, finding our critical t value. Well, the problem told us to run this two-tailed. We were instructed to use an alpha level of 0.05. And of course, the third thing we need to look up our critical value is our degrees of freedom. We're told that the sample size is 6, so our degrees of freedom is 5. So based on that information, lost all my stuff here. Based on that information, we look that up in our t-distribution table, as always. And we find that the value of our critical t is equal to, right sideways here, is equal to positive or negative 2.571. All right, that's our step 2. For step 3, we do our math. And for part A, we're told that the sample variance is 54 points. So that's just given to us. We don't have to calculate that. So that saves us one calculation. So we're going to use that then to calculate our estimated standard error. Remember, estimated standard error measures the same thing standard error measures. How much difference to expect between the sample mean and population mean due to random chance alone. So our estimated standard error, we know the formula for that is sample variance over sample size and then square root it. So when we compute that, plugging in our variance of 54, our sample size is 6. Remember, not degrees of freedom down there, the full sample size. Dividing that by 6. So 54 divided by 6, and then square root, we end up with 3 points of error. And then the t-statistic itself, the sample mean was 72 points. The population mean is given to us as 80 points. And we divide that by our 3 points of error. So we get a t-statistic of negative 2.67. Well, if we look at our roadmap over here, negative 2.67 is going to put us over here. So for step 4, our decision is reject the null hypothesis. And just for practice, if we wanted to write that in APA format, we would say that we have a t of 5 equals negative 2.67, semicolon, p less than 0.05. So that's our answer for 14A. 14B is essentially the same problem, but the variance is going to increase. In part B, variance goes from 54 points to 150 points. This is just another example of working our way through the mantras. If variance goes up, error goes up. And if error goes up, our t goes down, and it will become less likely that we'll reject the null. Again, as always, remember when we say the t value goes down, we mean closer to 0. So we're going to expect that this final t-statistic of negative 2.67 should be closer to 0 as we compute this. And maybe we'll get to reject, and maybe we won't. Well, step 1 is the same. The hypotheses didn't change. So the alternate hypothesis is still that the treated population mean will not equal 80. The null hypothesis remains that the treated population mean will equal 80. Our critical t-values don't change. We didn't change sample size, so degrees of freedom didn't change. We didn't change tails or alpha level. So step 2 remains identical. The part that's going to change for sure is here in step 3. So now, again, our sample variance has changed from 54 points given to us as 150 points. So now 150 divided by 6 and then square root. And we are going to get 5 points of error now. We had 3, but variability went up, so error goes up. Now, the sample mean and population mean is the same, so we still have a negative 8 in the numerator. But now we're going to divide by 5 points instead of 3 points. And in doing so, our t-statistic moves to negative 1.60. So absolutely, it did get closer to 0 than it was. So if we check against our roadmap here, against our graph, we can see that a negative 1.60 isn't going to make it anymore. We no longer reach the critical regions over here. We're in the body. So our decision is going to have to change to fail to reject. Now, just because we increase this doesn't mean it will always happen that we switch the decision. We still have to check it. But in this case, that's absolutely what happens. And so this part remains the same, but we've got to change the symbol for the decision. If we failed to reject, then we know that our p is greater than 0.05. Our odds of making a type 1 error are greater than 5%. So that is 14b. And so C asked, part C of it, comparing your answers from parts A and B, how does the variability of scores in a sample influence the outcome? In other words, the decision. Well, we can see, again, it's really just saying our mantra again. If variability went up, then our odds of rejecting the null hypothesis go down at the end. And that's exactly what happened here. And then lastly, to make sure we're practicing both one-tailed and two-tailed, the instructions said to redo part 14A, just part A, and write it as though it was a one-tailed hypothesis test and that we are predicting a decrease in scores. The problem is not written to be run as a one-tailed test. And you can tell because it says to run at two tails, and it doesn't talk about whether we're predicting. It's really a pretty generic example, whether we're predicting scores to go up or down. So because I know scores went down, that's why I'm having us predict a decrease in scores. So for step 1, the alternate hypothesis is the treated population mean will be less than 80, and the null hypothesis is the treated population mean will be greater than or equal to 80. So, just those changes in the symbols for our hypotheses, going from 2 tails where our alpha level is split to 1 tail where the alpha levels are combined will certainly change our critical t's. So for step 2, we now are running a 1-tailed test, keeping the alpha level at 0.05, and our degrees of freedom is still 5. We're not changing the sample size, so we still have the same degrees of freedom. But that's going to move our critical t when we look that up in the book, we're going to see 3.365. And negative. Why negative? We're predicting a decrease in scores. Again, notice that if we think of this as an arrow, it's pointing to the left side of the curve, so we're looking for negative values. Oh, I lied. I'm misreading my thing. I'm sorry, it's a little far away. I thought that number was weird for 0.05. My mistake, I apologize. Alpha level was 0.01. That's why it's so far out. I thought, well, that's weird. So that's step 2. 1-tailed alpha level 0.01, so I made 2 changes in that. Degrees of freedom 5, so our critical t is negative 3.365. So that's a pretty big change, right? 3 1/3 standard deviations out. Oops. I'm drawing this for positive and negative, aren't I? Now, for step 3, the math didn't change from the 14A the first time. Again, it didn't change any of the data. We're just changing the predictions. So the values, the answers for all the computations in step 3 are the same. Our sample variance is still 54 because it's part A. Our estimated standard error is, on the other side of the paper, is 3. And our t-statistic is still negative 2.67. So if we look for that value here now, negative 2.67, again, we're going to see that we're going to miss this critical region. We're going to miss that target. We didn't get far enough away from 0 to cross that threshold of 3.3, negative 3.3. So for step 4, our decision is to reject. Oh, I'm sorry, fail to reject. I'm making lots of mistakes here, aren't I? Fail to reject. And writing that in APA would be just like we've always done before. A t of 5 equals negative 2.67, semicolon p greater than 0.01. So those are your answers from the lab assignments for Chapter 9. See you in Chapter 10.